And I also like to thank Renzo for giving me the opportunity to talk about my work. I'm going to talk about stable knots and links in electromagnetic fields, and this is work that's supported by the European Union with the Marie Curie Fellowship. This is the outline of my talk, so I'll start with an introduction where I explain what I mean by stable links. Then I'll talk about Bateman's construction, which I will use to prove that every link type can be obtained as a stable link. And if I have time, I will talk about some current and future work. Okay, so this is something that you'll probably know. So a knot is a closed loop in three-dimensional space without self-intersections. And if you have multiple components, they form a link. So here you have a picture of a knot. There's a picture of a link with two components. And we study them up to ambient isotopy. So they're equivalent. Two links are equivalent if you can take one of them, deform it smoothly without any self-intersections until it looks exactly like the second link. And I'm interested in knots and vector fields. So you just consider a vector field on R3. And if you have a closed flow line, in other words, a periodic orbit of this vector field, then that will correspond to a knot in R3. Namely, you have a knot in R3 where this vector field is everywhere tangent to it, as indicated in this picture. And of course, if you have multiple closed flow lines, you get a link. And the vector fields that I'm interested in are time-dependent electromagnetic fields. So you actually have two vector fields, E and B, and both of them are time-dependent. And you can combine them in the Riemann-Silberstein vector, which is a function from R3 plus 1 to C3, such that the real part is the electric field and the imaginary part is the magnetic field. And of course, in order to have any physical meaning here, this function has to satisfy Maxwell's equations in vacuum for this work, which determines the time evolution of the electric and the magnetic field. Just like on the previous slide, you can now look at the knots that you find in these vector fields. So in particular, at every moment in time, E and B are just vector fields. So any closed flow line will give you a knot. And another way that you can obtain knots are these nodal knots. You look at, again, one fixed moment in time, and you look at the set of points where the field is completely zero. So both the electric field and the magnetic field vanish at the same point. And if this set is a knot, then sometimes it's called nodal knots or vortex knots. Both of these refer to one fixed moment in time. What I'm interested in are stable knots. So I don't want to have a knot just in one moment in time. I want to have a knot for all moments in time, such that when you look at the time evolution of these links, they are allowed to move around in space, grow or shrink, but they should always have the same link type. And the main result is that you can do this for any link. More specifically, you start with any given link of n components. You can choose any subset of its components, which will form the electric components, and the remaining components will be the magnetic components. And the theorem then says that for any such link, there is an electromagnetic field. In particular, it satisfies Maxwell's equations, such that this field has closed field lines in the shape of the given link, namely such that the components that you chose for the electric field are formed by closed electric field lines, and the remaining components, the magnetic components, are formed by a set of closed field lines of the magnetic field. And these are stable. So this is true for all time. And like I said, the time evolution is smooth. So in particular, you can choose any link for the electric field and any link for the magnetic field, and you can choose how these two links are linked with each other. Another remark, this subset of components that you choose, it doesn't have to be non-empty or proper. It's just a technicality. An important aspect of this is the time evolution of these fields. In order to make sense of the time evolution of field lines, the time evolution of these fields is given by push forwards by a smooth one-parameter family of diffeomorphisms, where phi0 is just the identity. We'll come back to this and another interpretation of this time evolution of these fields. So just to illustrate this, here's an example link with three components. You can pick for example, these two as the blue electric components, and then this figure 8 knot would be the magnetic component. And the theorem says, okay, now you have an electromagnetic field such that the electric field has closed field lines in the shape of these two blue curves, and a closed field line of the magnetic field of this figure 8 knot. And now when you press play and the field evolves according to Maxwell's equations, you always have closed field lines, and it always maintains this topological structure. I also have some results about nodal knots, but it's not really the topic of this talk, but I just want to mention them. So you can also show that you can realize any link type as a stable nodal link. So you have an electromagnetic field such that when you look at the vanishing set, the zero set at any fixed moment in time, you get the link that you started with. This result and the previous one with the closed field lines, these are existence results. So they don't tell you explicitly how to find these electromagnetic fields. I also have some construction here, which is a bit weaker than this one. So it realizes any link type as a sublink of a stable nodal link. By explicitly construct, I mean you can actually write down an analytic expression for the electromagnetic field, and this will have a stable nodal link, L prime, and a subset of the components will be the link that you wanted. Okay, so now I'll talk about Bateman's construction. And for that, I first need this function alpha beta. So this is a function from R3 plus 1 to the 3 sphere, where I think of the 3 sphere of unit radius as sitting inside C2. So both alpha and beta are functions that take values in the complex numbers. And when you take the moduli squared and add them together, you always get 1. So the image is on the unit 3 sphere. And they have these explicit formula, which is not that important. The important part is the geometric interpretation of these maps. For t equals 0, these maps are just a mirror reflection in R3 by the y equals 0 plane, followed by the inverse of the stereographic projection. So you map from R3 to S3. And in particular, this map for a fixed value of t will extend to a diffeomorphism from R3 and the point at infinity to the unit 3 sphere. And Bateman's construction that I mentioned earlier goes as follows. You can pick any functions f and g from C2 to C as long as they are holomorphic on some neighborhood of the unit 3 sphere. And then you can construct an electromagnetic field as follows. You compose f with this projection map alpha beta, and you take the gradient with respect to the 3 spatial variables. You do the same thing with g, and then you take the cross product of these things. And well, you get this function bold f. And the important result is that this actually is an electromagnetic field. It satisfies Maxwell's equations. And furthermore, it has a property that it is null for all time, which implies that the topology of the nodal links and the topology of all the flow lines is preserved for all time. And now I come back to what I said earlier about the time evolution. One way to view this is, okay, you have this one parameter family of diffeomorphisms, and the fields at a time t are just a push forward of the fields at t equals 0. Another way to interpret this is, instead of looking at time-dependent fields on R3, you have 2 vector fields, which I also call E and B, which do not depend on time, and which are vector fields on the 3 sphere instead of R3. So these do not depend on time. The only thing that changes with time is how you project these vector fields from S3 to R3. And well, both interpretations explain why the topology of the fields does not change with time. So this has been used in the past to find electromagnetic fields with knotted flow lines. This is work by Kedia, Bialynicki-Birula, Peralta-Salas, and Irvine. And they found that if you just pick f to be z1 to the p and g to be the z2 to the q, where z1 and z2 are the complex variables and p and q are natural numbers, and you apply Bateman's construction to this function, you get an electromagnetic field where both the electric and the magnetic field have a closed field line in the shape of the PQ torus link. Those of you who know about the Hopfion by Rañada, where this is a special case of this, For the Hopfion, you have the electric and the magnetic field have the property that all of the field lines are closed, and any pair of them form a Hopf link. And you get the Hopfion by choosing P and Q equal to 1. I want to use Bateman's construction, but I will rewrite it slightly. So instead of using F and G here, I just write it as the product of H and then the cross product of the gradients of the individual components, alpha and beta, where H is given explicitly like this. And since Bateman's construction works for any arbitrary holomorphic F and G, it also works for any arbitrary holomorphic H. So if you write it like this, there's a very interesting relation. You can prove very easily that Maxwell's equations for fields like this are equivalent to the tangential Cauchy-Riemann equations on S3 for the function H, which just means that this really is a holomorphic function. Okay, writing this field in this form means that you have reduced the question of how to construct stable links to the question of how can you find a holomorphic function H such that the corresponding electromagnetic field has these knotted field lines. And in order to prove that you can always do this, I will need some tools from contact topology. This will not be very complicated or anything. It's very basic. I just go through the fundamentals, really. So the definition is a contact structure on a 3-manifold. You have a smooth, completely non-integrable hyperplane distribution of the tangent bundle. In other words, for any point in your manifold, you have a plane in the tangent space of that corresponding point. And as you vary the point in the manifold, this plane is supposed to vary smoothly. So this is this, smooth. And the condition that it should be completely non-integrable just means that there should be a certain amount of twisting as you vary the point in the manifold. So this picture illustrates this in R3. At every point you have a plane, and as you vary the y coordinate, this plane twists. And actually, there is only really one contact structure that I am interested in, and that's the standard contact structure on the unit 3 sphere. And there's two ways to define this, and both of them will be useful for us. The first one is the contact planes are precisely the complex tangencies to the unit 3 sphere. And maybe a bit more intuitive is if you look at the Hopf vibration from S3 to S2, you look at the normal directions to the fibers of the Hopf vibration. So any point on the 3 sphere will lie on a unique fiber, and the contact plane will be the normal directions with respect to the round metric on the 3 sphere. If you have such a contact structure and you have a link in your manifold, you can look at how your link is positioned relative to these contact planes. And a very useful definition for us is this one. A link is called Legendrian if it is everywhere tangent to these contact planes. And the reason why I go through all of this and why it matters in the context of Bateman fields is the following. If you have an electromagnetic field that comes from Bateman's construction, then for any value of t, the closed flow lines of E and B are projections of Legendrian links. What I mean by this with projections of is, again, you look at the corresponding fields on the 3 sphere, which do not depend on time. Their closed flow lines will be Legendrian links, and the actual flow lines that you see in R3 will be the images of these Legendrian links under the projection maps alpha beta inverse. And I will go through the proof, not in detail, but in general, for all of these proofs, the details are not the important part. The important part is that there are these connections between different areas of mathematics and physics. So we've already seen Maxwell and holomorphic functions, and now we have contact topology. So one way to prove this for t equals 0 is you look at the normalized Poynting vector field, so the normalized cross product of E and B. And the first thing that you see is that if you have a field that comes from Bateman's construction, you always get the same Poynting vector field. It does not depend on the choice of H. And the field that you get for t equals 0 is, when you take the push forward to the 3 sphere, is exactly tangent to the fibers of the Hopf vibration. So now when you look at E and B, they are by construction orthogonal to the Poynting vector field, as are their push forwards. So that means they are orthogonal to the fibers of the Hopf vibration. And when you think back to the definition of the standard contact structure, that means that these flow lines must be tangent to the contact planes. So in particular, all the closed flow lines must be Legendrian links. Here's another way to prove this, which allows us to generalize this to other values of T. When you just write out the definition of E and B as the real and imaginary part of F, you find that these are linear combination of these two vector fields, the real part of the cross product of alpha and beta and the imaginary part. And now you just look at the corresponding fields on the 3-sphere. So you calculate the push forward by this projection map of some multiple of these fields. And you find that these are, well, two vector fields, V1 and V2 on the 3-sphere, and they form an orthonormal basis of the standard contact structure. And since E and B are linear combinations of these two basis vectors, that means they must also be Legendrian vector fields. And you can do the same thing for other values of T. You again obtain basis vectors for some standard, for some contact structure, which is equivalent to the standard contact structure, but maybe not equivalent on the nose. Okay, so what we've done so far is you start with an electromagnetic field and you obtain from it Legendrian links. What we would like to do is go into the other direction, start with a Legendrian link and get an electromagnetic field from it. And the first thing we need to define a certain function, which will be a stepping stone towards this holomorphic function small h. So we have the standard contact structure, we pick a Legendrian link, we pick a subset, and we also pick a nowhere vanishing section of the tangent bundle of the link. And because it's Legendrian, this tangent bundle lies inside the contact planes. So then we define a function which takes values in the complex numbers, and it's defined on the link. And well, the tangent vector lies in the contact plane. V1 and V2 form an orthonormal basis of the contact plane. So you can express the tangent vector in terms of V1 and V2. And this is exactly what you do. The real part and the imaginary part of H will be the coordinates of the tangent vector with respect to the basis. And well, you do this for the electric components, and the magnetic components will be the rotated basis. So you have defined this function capital H. We need this following lemma. If we have this link, the section of the tangent bundle and the function capital H, then if you have an open neighborhood of the 3-sphere and a function that is holomorphic on this neighborhood and has the property that when you restrict it to the link, you get back the function capital H, then you can use this holomorphic function in Bateman's construction and you get an electromagnetic field that has this topological property that you want. So it has a closed field line in the shape of the link that you wanted. So now the question is, oh yeah, so the previous is direct calculation. You just look at the field at a point on the link, you plug in the definition, you use that on the link H is the same as capital H, and then the definition of H shows you that the magnetic field is just a push forward of the tangent vector. In other words, it's tangent to the link, and it's the same thing for the electric field. So now the remaining question is, can you do this in such a way that this function capital H, which is only defined on the link, extends to a holomorphic function on a neighborhood of the 3-sphere? And another lemma that I'm not going to prove, but it's fairly intuitive that this works. Every n-component link type has a real analytic Legendrian representative and a nowhere vanishing section of the tangent bundle, such that no matter which subset of its components you choose, the resulting capital H is also real analytic. Quick remark, technically, we should exclude those links that pass through this point 1, 0, because that's the point that gets mapped to infinity with our stereographic projection. But yeah, it's not difficult to see that this is not a problem. And then we used this result by Burns and Stout. They studied exactly this question of when do you have a holomorphic extension. So they defined this property of being an analytic interpolation manifold. And they say a real analytic submanifold of C2 that is contained in the 3-sphere has this property by definition if every real analytic function which is defined on the submanifold extends to a holomorphic function on a neighborhood of the 4-ball. In other words, also on a neighborhood of the 3-sphere. And they characterize the submanifolds that have this property. The defining property is exactly, so you have an analytic interpolation manifold if and only if it's tangent bundle is contained in the complex tangencies of the three-sphere. And now you think back to the first definition of the standard contact structure, and we can put everything together. We take our Legendrian link to be the real analytic submanifold. We've constructed it in such a way that the function capital H is real analytic. And the condition that the tangent bundle of the link is contained in the complex tangencies is precisely saying that's a Legendrian link. So that means that by Burns and Stout, L is an analytic interpolation manifold, and in particular, this function capital H has a holomorphic extension. You use this holomorphic extension in Bateman's construction to obtain the electromagnetic field that you wanted. Okay, and that proves the theorem, and now I can just very quickly point out another connection to some interesting work. So this is the definition of a totally tangential C-link by Rudolph. So a link in S3 is totally tangential if there's a holomorphic function from C2 to C, such that when you look at its vanishing set, it intersects the three-sphere in the given link, and this intersection is everywhere tangential. The reason why this is important in this context is that Lee Rudolph proved that the property of being a totally tangential C-link is equivalent to being a real analytic Legendrian link. So exactly the kind of curves that can appear as the closed flow lines in Bateman fields. And well, he also proved that every link type arises, which also follows directly from this. Here's one example of this. The P minus Q torus link you get as a totally tangential C-link by looking at this holomorphic polynomial Z1 to the P, Z2 to the Q minus 1. And you need to look at the three-sphere of a certain radius, which will depend on P and Q. And you get this torus link as a tangential intersection. The interesting thing about this is, as far as I know, this is the only family of examples where we know this function capital F. And when you think back to electromagnetic fields, again, we have the situation, we know that it exists for every link, but the only examples that we have are the torus links. So here are some current projects where we already have some partial results. Together with Lee Rudolph, we're looking at the relation between this holomorphic F, which defines the tangential intersection, and the holomorphic H, which defines the electromagnetic field. We already have some results about constructions of such tangential intersections, and we hope that this will allow us to actually give you constructions of the electromagnetic fields. And together with Daniel Peralta-Salas, we were looking at relations between link invariants that come from contact topology and properties of the electromagnetic field. In particular, we found that the field can be non-vanishing if and only if the corresponding link has a 0 rotation number, which is a contact invariant. We're also looking at Seifert vibrations, so these would be generalizations of Rañada's Hopfion. And we're also looking at the possibility of getting invariant tori of these electric or magnetic fields. And I'll stop there. Thank you.